All right. Let's continue and finish up notes part one. So our second page, excuse me, looks like this. These sentences here, I think, are going to be intuitive to you. So to move something, we push on it, right? Obviously. And the more we push, the more the thing moves. So imagine there's a desk on the floor and you're pushing on it, okay? You want to change seats or move your desk to the corner or whatever. So to move something, we push on it. The more we push, the more it moves, obviously, and the more the thing is, meaning the heavier, right? And so it's a big desk instead of a small desk, the less it moves for a given push. So if you push as hard as you can on a small desk, it'll move fast, and if you push as hard as you can on a big desk, it'll move slowly. And so I think that this is like common sense stuff, all right? And the cool thing, one of the things I love about physics, is you can take common sense and you can just kaboom, turn it into an equation, and that's actually physics, which I think is cool. So Newton's second law says the most common way of seeing this, I think, is F equals ma. Sometimes dividing both sides by mass, we can get the acceleration is force divided by mass. So the acceleration of an object, we'll define the variables and stuff. On our equation page, this looks like this. And so there's some technical stuff. So we have A with a little arrow over it, and the little arrow indicates that it's a vector quantity, meaning there is some direction implied. And then, so the acceleration is going to be the sum of all the forces. And force also is a vector quantity. There's a direction to it, whereas mass is not, so there's no little arrow. So let me write this so that we remember later. So those things indicate vector quantities. And so it's written like that, or just like this, where we have F net. So net force, we're going to talk about real soon, I think later on this page or whatever. So these are the different ways that you'll see Newton's second law. This is how it is expressed on your formula page. For the most part, you'll be substituting in there, just kind of simplifying it. Okay, so here's an example. Calculate the force required to accelerate. So we're looking for force, a push or a pull, and it's measured in newtons, required to accelerate a 1,000 kilogram car at a rate of half g. And g is the acceleration due to gravity. So when we see something like 5g, right? So this would be for like airplane pilots, or I mean fighter jet pilots, right? It's kind of difficult to withstand. There's some funny videos if you look online about people in the military undergoing tests where they experience large accelerations. So anyway, half g is 1/2 of 9.8 meters per second squared, which is an acceleration of 4.9 meters per second squared. Okay, and the acceleration due to gravity is in a downward direction, obviously. We don't know in which direction this thing's being accelerated, so the positive or negative doesn't really matter at this point. But we're looking for force, and we're accelerating some mass. So if we were being good about showing our work and being detailed, we would say, all right, we know the mass is 1,000 kilograms, and we're looking for force, question mark, and we know our acceleration is 4.9 meters per second squared. So I've listed the given information. I might even draw a diagram where it's like 1,000 kilograms, force equals question mark, and then we could say acceleration is 4.9 meters per second squared. So there's my diagram. And then when we go to substitute in to the equation, Newton's second law, F equals ma, we know that the force is what we're looking for, and mass is 1,000 kilograms, and acceleration due to gravity, sorry, half of that is 4.9 meters per second squared, and we would end up with 4.9 thousand, meaning 4,900, and this is measured in newtons. And so I think we're going to discuss what a newton is, but basically, if mass is in kilograms and acceleration is in meters per second squared, force is going to be in newtons. Okay. Maybe we already talked about that in the previous. Sorry, it's another day, and I'm making this video lesson. Okay, so and that's a lot of newtons. That's about 1,000 pounds. Okay, I mean that's a large force. So do the same for a 500-gram apple. So this is kind of just practice with units. And so I'm going to skip the part of writing the given information in the diagram, being the bad student that I am. And so if we were doing force equals mass times acceleration, our force is equal to, and mass, be careful here, you have to know grams, kilograms, centimeters, meters, that kind of thing. 500 grams is 0.5 kilograms, so there's our mass. And here's our acceleration, and so our force would be half of 4.9. What's that, 2.95? I'm going to check on the calculator here. 2.45, that's what I meant. 2.45 newtons. Right. Okay. Oh, good. Here we are. What exactly is a newton? So I'm looking at this because this question arises. What exactly is a newton? So we can say two things, and I'm just going to write this in the margin here. I like how I have infinite scratch paper. So a newton is, it can be defined as a measure of force. Okay, and so it's a measure or it's a unit that we use for force. It's basically the force required to accelerate 1 kilogram at 1 meter per second squared. So we're basically using F equals ma to define what a newton is, where we're saying, because these are sort of fundamental quantities, a kilogram, fundamental quantity of mass, and then acceleration is measured in meters per second squared, and meters and seconds squared are fundamental quantities. So we define the newton in terms of kilogram meter per second squared. So you could also say, and I like this if you're doing some unit analysis to help you figure out your equation or whatever. So newton is equal to a kilogram meter per second squared. That will probably be helpful. Okay. Moving back, so I think we're going to do some experimentation with this. The question, so we have a couple different masses hanging from the ceiling. This one is shaded in, that indicates a solid surface. What is the tension in each section of string? And so we have different, so we have this string and this string and this string, and what's the, which is experiencing the greatest force? So by tension, tension is sort of defined as a force in a, and this could be string, cable, chain, whatever, something like that. And so that's only going to be a pull. You can't get a string to push. Okay. So this would be these arrows are not good. I should have drawn them like this. Let's go. So we have a short arrow, and we have a larger arrow, and we have a larger arrow in terms of what the tension actually is. So another form of force equals mass times acceleration is this, weight. And so we've talked about how weight is a word we use to describe the force due to gravity. And our weight depends on our mass, and it also depends on where we are. For example, if we were on the moon, we would weigh less. If we were on Jupiter, we'd be totally dead, and we would weigh more. So this g, acceleration due to gravity, can be expressed like this. So the force due to gravity is weight, our mass is our mass, and the acceleration due to gravity on the surface of Earth is 9.8 meters per second squared. So this formula can be used to, it's not necessarily correct to say convert between newtons and kilograms, because that's location dependent, but it is what we use to calculate our weight. So we're doing the same for these things. And I'm going to zoom in now. So if we figure out the weight of each of these things, and I'll draw a downward arrow, so this is a downward force, the weight of the 2 kilogram mass is mg, so 19.6 newtons, and the weight of the 3 kilogram mass is mg, and so that would be 29.4 newtons, and the weight of the 4 kilogram mass, etc., is, and that is 39.2 newtons. So, if you consider the strings, this string is supporting 39.2 newtons of weight. So, let's find ourselves a different color. Let's see. Oh yeah. Alright, so this part of the string is supporting a force of 39.2 newtons, so the tension in the string would be that, 39.2 newtons. This string, however, is supporting both the 3 kilogram and the 4 kilogram mass, and so the tension in that string would be, this is a 39.2, because it has to support that, plus it has to support the 29.4. Both of those added together. So 29.4 plus, you're probably following along with your calculator, 68.6 newtons. And then the top string is supporting all three. So all three, and I think, because I don't have much space, I'm just going to, so it'd be 19.6 plus the bottom two, which would be like this. And so 68.6 plus 19.6 would give us, this is supporting a weight of 88.2 newtons. Okay, so notice how I'm using newtons for weight and force, and I'm using kilograms for mass. Great. Alright, I think that's it for this. Thanks for listening.